So how do we go about it?
So you have to share your screen.
Okay.
You have to share your screen. Sir, please wait just 2 minutes, then we'll
Yeah,
start.
sure. Will do.
So, Madhu madam, are you there? I think she is doing. আচ্ছা মধু ম্যাডামের সেশনটা কোনটা ছিল দেখো তো উনি এখন ওখানে আছেন WM2 দেখো তো ওখানে কতক্ষণ বাকি ভলান্টিয়ার কে আছে You can make it live now.
Yeah, it's live. It's live already.
Okay, fine. So now, good afternoon to all the participants and our today's keynote speaker, Professor J.K. Singh from IIT Kanpur. So I welcome you, sir, and thank you very much for accepting our invitation to deliver keynote address in SCMCon 2020 in this virtual mode. Also, I'd like to thanks to Dr. Madhu Agarwala from NIT Jaipur. She is the joint secretary of IICG. So she requested to our today's speakers, Professor Singh, and sir has accepted. So thank you very much once again. So now, sir, you can start today's lecture. So it is already live in YouTube.
Thank you. Thank you very much. I'm audible? Am
Yes,
I? Okay.
absolutely.
Thank you. Thank you, Professor Madhu and Professor Ghosh and all other organizers for giving this opportunity. And particularly to my younger colleagues for being here to listen to what I have to say. So I thought about this topic, and I thought it's better to just give a brief background of what we are trying to do in general, where this field is heading, particularly from the perspective of chemical engineering. And so I will just go through a bit of what we are talking about, and a bit of history, and I will try to add on to some of the work which we are doing in order to explain a bit how we are using molecular simulation to explain the phenomena from the point of the thermodynamics, and as well as from the point of view of some applications. And what challenges we are going to seek or in general to make this particular technology, or rather the techniques, and methods to be part of our mainstream chemical engineering, just like, for example, the COMSOL and CFD and other things have come. So that's the idea behind this talk, and this is mainly for the student community to see, where we are and what was the past and where we are heading for. Okay, so the question first is why molecular simulation? Okay, so to put down very simply, it's basically to predict properties, of mainly the new materials. Of course, the existing materials can do, but is mainly meant for predicting some properties of new materials, which are not that easy to do that in experiments. And the other objective or the purpose of using such a tool or methods is to understand phenomena on the molecular scale. Okay, so I'll talk about a bit of that. And the other thing is to test a theory or methods. That means already some phenomena or the results are very, very well known. And if you want to design a theory, you can test using molecular simulation to check whether the theory is predicting the right thing or not. So that's the three main category under which molecular simulation methodology works. Okay. So let's give an example that why do you bother about this thing. So let's talk about this. For example, finding out the melting point of ice. Okay. And of course, you can do that easily. This works pretty easy in the experimental and the lab scale. But if you really want to measure, let's say, ice property somewhere in extreme harsh conditions, such as Mars, then how do you go about it? Okay, in fact, you'll see that this is a dry ice in Mars. And if you go to the basic thermodynamic phase diagram, you will see, well, typically you have the pressure of 1 atmosphere. So you can see this phase transition from solid to liquid and to vapor. Whereas in the case of Mars, the pressure is so low that it acts like a dry, just like similar to CO2 in normal conditions here, which you observe as in a lab scale. But in the case of water at Mars, it will behave like simply dry ice-like, because it will not undergo from solid to liquid because of the low pressure. Now, such experiments are not that trivial to do that. And of course, many other examples are there where you would like to predict such properties. So the idea is to simulate such a system. And that's what we wish to predict macroscopic property of many body system. The question is, can it be done? Okay, can you represent water into some models and then predict the property? So that's where the relation of macroscopic world and thermodynamics comes into the picture, and through a mean called statistical mechanics. So what we are talking about is a different macroscopic property. So this can be categorized in mechanical properties and thermophysical properties. Mechanical properties would be something like elastic moduli strain relation, tensile strength, and so forth. And thermodynamic property would be simple density, viscosity, surface tension, the phase diagram, and many other things which we often learn in our chemical engineering thermodynamic course in the second or third year, okay, and as well as in the advanced graduate level courses. So how do you predict properties? Well, in principle, if you can follow a certain body, let's say if you're aware of the velocity of a certain body, then you can also predict its future behavior. In the case of molecular world, you would have to predict many bodies, not just one. So in principle, if you have been provided a velocity and interaction of particles, then you can use a classical, Newton's equation to do that. And if you can predict the properties or by following the particles or atoms, or as if you have the means to find the trajectory of each of the particles and in their interaction. So, so everything boils down to this simple equation. But is it so simple? Well, it turns out that if you want to simply predict, let's say, pressure, you can represent this pressure in terms of number of particles, which is n here, the Boltzmann constant, the temperature, and the V is the volume. This is basically nothing but ideal gas contribution of a given system. And then you have this term which represent due to the interaction between the particles. And if U, which is your internal energy, let's say, if you put this to be 0, you will get the ideal gas term. This is nothing but the interaction energy of particles. Okay, so if the particles are not being interacting, you basically, this whole term will be zero, and what you're going to get is the ideal gas term. And this S here is basically nothing but the positional coordinate in the scale coordinate form, and N is a number of particles. Now this is of the order of Avogadro number. Now this makes life a little difficult. If it is a two body only, then you can actually do a simple, coding, and you can do that. But if it is a 10 to the power 23 kind of order of the particles, how do you actually model? And that's where the computer plays a big role. Okay, before the advent of the computers, people were just using alternative ways to find out the properties. So they were using spatial theories. They were constructing simple models, just like a molecular Lego. So the earliest model of a liquid was something by Bernal, where they used this ball bearing model, where they put this in the form of a closed packed system, and this was used to understand how atomic liquid would form. Okay, it was not feasible to model a liquid in 1960s or 50s. In fact, in 1953 was the first Monte Carlo simulation was done in order to even get the equation of state. Now, all of you know the equation of state. Okay, you know the van der Waals equation of state, which was developed much earlier. But mathematically and computing wise, if somebody, in terms of really taking particles into the system and following the trajectory, the two-dimensional, not even three-dimensional, two-dimensional system was first done in 1953, where the equation of state of interactive individual molecules were described. Okay, this was nothing but two-dimensional rigid system. It was only repulsive forces. And that was the first equation of state which was developed by none other than this Metropolis Rosenblatt and Taylor people. Okay, so that's the system which we are working on. This is a classic people who have developed this thing, and what we see as a simulation standard is mainly contributed to them in terms of the developing of algorithms and so forth. But around the same time, there's a lot of argument about how does the liquid converts into solid, or that means what is the origin of a solid liquid to solid transition. And in the process of that, the same Elder and White, they developed the first MD model. That means the first Newton equation converting into the language of programming and trying to use the forces and trying to follow the trajectory of the particles. And in the process, using the equation which I said, the pressure, okay, the equation which I just mentioned, the pressure here, this was solved to get this equation, which is nothing but the compressibility factor as a function of the volume ratio. So the V0 stand for the size of the particle which they used. So they developed this first again equation of state. That was in 1957. Okay, again there's argument of the origin of this phase transition was in picture. Of course, that was clarified. The condensation, the crystallization was they clarified that the repulsive forces are very important for solidification. Around that time, 1964, of course, this methodology started coming into that. In 1964, the first molecular dynamic simulation, that means the equation of motion solving and trying to put it into computers, calculating the interactions and solving the properties of a system was first done by Rahman in 1964. This was for argon. And apparently Rahman originated from Hyderabad, and he's known as a father of molecular dynamics. And on his honor, American Physical Society annually award for the best outstanding achievement in computational research. Okay, you will see this picture of that Rahman. Okay, and now later on, of course, the computer started becoming better. This was earlier started on the 24-bit transistor-based CDS 3000. And of course, the well-known Cray system came around that time as well. Later on, Rahman and Stillinger came up with the first simulation for water. Okay, and that was a really big jump from a simple argon, though it's not that straightforward simple because the three-body interactions are there as well. But it coming to hydrogen, where the hydrogen bonding plays a big role, was a big leap. And if you fast forward 1974, 3 years later, the McCallum, Gellin, and Karplus came up with the first molecular dynamics of a protein, which was published in Nature at that time. And later on, the same set of people, one of them, Karplus, won the Nobel Prize in chemistry. And his main contribution, apparently, has been the model development for the complex chemical systems. And that's where essentially brings the contribution of molecular simulation in that sense. Okay, so that is where we are now. If I just want to fast forward, this is 2013, and then we move to the 2000. We just show that the number of people who are using molecular simulations is growing exponentially. If you just look at it, this is a review of AICG, which was done a couple of years back, and 2009. You could see clearly that how exponentially this got expanded, exploded. This is a basically MD publication per 1,000 papers in the science and engineering. Okay, in 1960-65, there was hardly any paper in that per 1,000 papers. However, in 2005, it was like 5 or 6, and currently, if you look at it, it would be like 30 or 40. In fact, now you will see that every other science and engineering paper, somebody is trying to understand or connect the molecular simulations, in the sense finding out the property at the molecular level and connecting to the phenomena. This field is still in infancy. It's still 50 years compared to 400 years of experimental science, and it's going to go a long way, and it will be well integrated with other tools in the future. Okay, so now the question which I started, that's a little bit of history. How is this going to be an engineering tool? I mean, has it become a mainstream chemical engineering tool in the way that the process simulations or finite element modeling are? Okay, if a main engineering tool is defined as a method of useful, practical, and accessible to the wide researcher, then does this molecular modeling and simulation fits into this definition? The answer to this question is basically depends on how do you want to use it. Okay, and that's where it's important to appreciate from the point of view of the science. However, from the point of view of application, there's a lot to be done, and there is something which we have to walk a long path in order to get that. So again, let us revise what we are talking about. We are talking about a computational use of computational methods to describe the behavior of matter at the atomistic or molecular level. Okay, so if you just summarize the methods in this domain, then I would like to just give you a brief idea of a time and length scale and where all these methods fits in. So this is basically time. That means that means whatever the phenomena you are interested in, that is a time scale of that, and the length of the system which you are interested in, that would be this. Okay, so typically, if you look at 10 to minus 4 micrometer and time scale of seconds, you prefer to use the continuum methods. Okay, where the phenomena is occurring in the seconds and so forth. That's the current state. People prefer CFD. You would like to use COMSOL or OpenFOAM, and these are the methods or tools which you're going to use that. But if you want to go down where the phenomena are more intricate, but happens at a smaller time scale, and you would like to involve or include more of a complex interactions which are part of the system, then you have to reduce the typical length and time scale. So you have methods such as quantum chemistry, ab initio methods, semi-empirical methods, and this atomistic simulation which I talked about, molecular dynamics and Monte Carlo falls in this one. And then if you want to coarse grain it, then you have this lattice Monte Carlo, Brownian dynamics, distributed particle dynamics. Well, this is pretty much now established now. Whereas this, it's still, I wouldn't say that it's very well developed, but of course, there's a lot of people who are working on this. And it's quite powerful if one want to understand the fluid behavior, structure, or dynamics of it, and a little bit time scale, which is larger than this. So it will miss out the interaction, but it is still, it does quite a good job. So if you're interested to bring from the electronic level to the devices, then you have to look at the electronic level, then you have to find out the properties, you have to scale up to the to the higher scale, and eventually you have to connect to the device. So essentially, there is now a mechanism, there is a way to do multi-scale modeling where you can take literally electron and atoms and molecules and understand each of them and bridge the gap and take it to the device. Now, there is not many groups in the world who are coming with a integrated platform to do that, but in time to come, this is going to be the reality. And I know a couple of groups who are very active in this, where you actually can start with electronic level and build the device, and you be creative in that by including and screening many things at the many levels before coming to the device or the product which you're interested in. So that's what we are looking for. We are seeking that some kind of integration and including all aspects of the length and time scale interaction to come up with the right kind of device with a very efficient means to achieve it. And that way you can, whether you want to do a drug discovery, you want to develop a new batteries, you want to develop new additives and so forth, this all can be done if you can include all these scales in a right manner. So the question is it still the mainstream tool for chemical engineers? Well, I won't say that. And there's a lot to be done in order to make it a mainstream. So MD, molecular dynamics and Monte Carlo methods are not yet, they are part of the many codes now, which was 10 years back, they was done. And now there are many softwares which they have included, they're free softwares. So, but there are issues, okay, because one is the techniques are not very well known to the chemical engineers at this point, and there's a lot of training is necessary. And this is not also a common course in the chemical engineering curriculum. That's another challenge we face there. Similarly, doing the Brownian dynamics or lattice Boltzmann or coarse graining methods are also something which is not yet widespread. That's another thing which we have to bring in order to make it useful in the chemical engineering curriculum and as well as in applications. Okay, and the third thing is that whatever the process design we're building up, or the equation of state, which is a part of ASPIN, another thing, we process the design softwares, that is not well integrated with the molecular modeling. In fact, many top schools, universities have a program where they integrate process engineering and molecular modeling, and that's something which is also going to come in the future. So this requires changes in the curriculum. This requires integrating with the industry, and that's where the third part is extremely important to make it valuable for the job scenario, where we bring in the knowledge at the university level, and thus the industry can also benefit from such kind of endeavors. Okay, so what normally molecular simulation activities are, one is a discovery level. So basically we try to search for new phenomena, simulate new materials such as nanotube metal organic framework. We have tried to understand nanoscale phenomena. For example, what would be the structure of water in a very confined conditions? How does, let's say, virus work in different scenarios? Explanation of phenomena, for example, whether, let's say, if we talk about COVID virus, whether it stays stays essentially on a surface, or whether it's going to repel. Then you have this phase transitions. You can understand various different phase transitions in a different environment. Similarly, many other properties. So I don't want to go into details of it because of the lack of time. But basically, this can predict many things if you are able to understand. If you have the right kind of interaction models of the molecules, that's one of the important things. The other thing which can be used is basically development and validation of the method and the model. You can develop the general force fields. The force will stand for the model for interaction between the particles. So you can develop these validations or develop these models which can reproduce the PVT data and transport properties of a different kind of fluids. Okay. So I'll just skip that because this is something which I've already told. You can also test the theory, as I mentioned earlier, like, for example, ideal adsorption theory, Stefan-Maxwell, regular solution, SAFT, and so forth, okay? And as well as the validation of difficult experiments, okay, such as crystal structure refinement, STM, AFM studies. These are the experimental techniques. You can also add on or support this kind of experiment. Okay, so I will give you some example of extreme conditions, and just to give you a flavor of particularly from my group what we are doing. There are many commercial and academic softwares, as I mentioned. These were not in existence in 15, 20 years back. These all got developed in last 10 years beautifully. And many are there used, for example, LAMPS is one which is maybe perhaps used by, I don't know, maybe 1 lakh people or researchers, pretty heavily used. This is a commercial software. So many open source softwares are there. We have our own software as well, which can be used by others. Okay, so let me just give you an idea what kind of impact these methods have created. So this is an example from Sipman's group, but it was published in 1993. So this was the first work which simulated the critical behavior of alkanes, and this was not that easy to obtain the alkane. So from this experiment, and this was a predicted value. So they developed a method called Gibbs ensemble Monte Carlo simulation, basically using the thermodynamic conditions as a criteria, and developed the Monte Carlo methods of moves to reproduce kind of to have this consistency as far as a Markov model is concerned, detailed balance. These are the terminology used in that. But the key thing was once they developed this, demonstrated its efficacy by calculating the phase diagram of basically alkanes to the point of C48, and that's something which was not possible to do that in experiment. And this is nothing but the vapor line, saturated line. This is the critical point, the field symbol. This is the saturated liquid. And they also looked into the critical density as a function of number of carbon atom in the chain. And of course, they obtain this maxima at around this. Now, as I said, this was the first, this was a prediction, absolutely. And later on, of course, the equipment, the experimental techniques came where they did indeed, they found that the behavior is in line with that. And that is why, this was a remarkable work which was published in Nature in 1993. Okay, so fast forward, I will just talk about something which we have been doing, which I have done for last, I think, last 10 years. This we started in 2000. So I think I have to, somehow it got shifted. Okay. All right. So this is basically a simple, let's say, phase diagram, which we everyone know is a pressure temperature diagram. And the question we started asking that, how does it will shift or will it change if we put the liquid fluid in nano confinement, such as, for example, a parallel plate with a difference in gap close to few nanometer. So we observed a shift in the transitions, such as solid liquid, vapor liquid, liquid transitions, they got shifted. But in addition, we observed that a new phase transition got, were observed depending on the nature of the surface on it. Okay, so let me just give you an example of what something which makes a very interesting phenomena in this. So this is an example from a paper in Nevin in 2004, where they observed a liquid gas interface between a nanotube, okay, and this is like multi-wall tube, and this is a water and this is the gas, and this is separated by 2.9 nanometer, okay, and this is a simple at room temperature. Okay, so what they did is, of course, they also calculate the critical point. So our interest was basically, if you have this interface which is forming, first of all, the question is that, is it literally the interface, or is it a bubble or so forth? There's a separate debate on that. But we wanted to calculate the phase diagram of a simple system like that. And that is what we obtained. So this is the first work which they did, and they obtained, they said that, well, water perhaps behaves like that. So this solid line which you see is a normal water temperature density phase diagram, whereas water and CNT behaves in this form, okay? So so our question was that, does it only behave with water or something which is true for many other system? And if it is, what would happen if we further squeeze it And do we get a two-dimensional behavior? What would be the condition of the transition from the bulk-like or three-dimensional behavior to two-dimensional behavior? So these are the questions which we were pretty bothered by that time. So we developed, we use extensive simulation method, and this is just a reduced unit temperature and density. And what I'm plotting here is basically a simple system, such as your argon-like system, not even water. Okay, so we have done for water, we have done for many systems. So this solid line represents a typical temperature density phase diagram. And what you see here is that different nature of the phase diagram as we squeeze the fluid from 40, bulk like to 40 angstrom, and slowly falling here is something like 40 nanometer from here to around 2 nanometer. So eventually this behavior, which is a very non-monotonous behavior, we observed, very complex behavior we observed for a simple fluid when we bring this fluid in the two plates and bring it very close. So it undergoes a non-monotonic change from a bulk-like behavior to a two-dimensional behavior, where this one which you see here is basically a two-dimensional system where the critical density is much smaller than the critical density or at a larger gap, and as well as critical density of the three-dimensional behavior. Okay, so there's a literally a very unusual behavior as you see, and later on we came up with a theory to explain this thing from the physics world to explain such a theory. So let me tell you what is the relevance of such a work in experimental or in industry. So this is a simple fluid which or lubricant which is used in a hard disk on top of it. And when your slider, which is a recording, in order to read the data of your which you record in your hard disk, it uses this kind of a slider, and there is a rotating disk which used in order to check the read and write operation continuously. So this is just an illustration. Now what happens that due to this continuous operation, if it gets dry, then the heat will there will be a lot of heat so-called will be generated, and that can create problems. So this is important to have a lubricant which doesn't dry up. So this gap is around 10 to 20 nanometer. So it plays a big important role to understand the liquidity, rather the liquid nature of the lubricant at this condition. So whether we would like to understand what would be the condition for liquid to solid transition for such a system. Another example comes from our joint cartilage. We all know that as we grow old, basically the lubricant, which is a soluble fluid, which can withstand the pressure up to 50 angstrom, 50 atmosphere, apparently gets dried at a later age, and does a lot of people get this pain, and arthritis and other aspect of that. So in order to replace this fluid, one would like to come up with a polymeric or some kind of fluid which can sustain such a pressure. And in that way also you would like to understand the phase transition from a liquid to solid thing. And this is where the molecular simulation plays a big role. So, so there was a lot of work in early 90s by Klein and other people, Granik and Klein. These are two different groups. They were talking about what would be the typical transition of such a system when you place a lubricant, or rather, let's say a simple example of alkanes confined into two micas. Okay, because they were doing this experiment of AFM, bringing a AFM tip near to the fluid. Okay, such fluid such as any alkanes or any other fluid on top of a mica system, and trying to understand the viscosity of such a system. Whether if the viscosity jumps by many fold, then this is indicative of phase transition from a very large gap D, which is a gap between the tip of the AFM and the surface of the substrate on which the fluid is kept. And if you bring it closer, then there's a viscosity jump indicating of an ordered system that is indicative of a solidification. Now, similarly, if you can represent this thing in the simulation, so what we did is we tried to develop this model and create this mica surface. And if you look at this mica surface, you can consider this top mica is basically nothing but the AFM tip. Okay, and the bottom mica is nothing but the substrate. Okay, so basically we try to look at. Let me see if I can see the movie. It looks like the movie is not playing for some reason. But what we show that, if you bring it, if it is cyclohexane, for example, it is a pretty much FCC lattice. If it is dodecane, it forms a different kind of structure. So we actually calculated the solid liquid transition for such a system. And it turns out that this is something which is not very unique to only this kind of system. You actually can put a simple molecule. It could be your argon, it could be your others, and they will behave more or less something similar, except for that if the chain molecules, they may behave differently because they will form a different kind of phases other than a spherical kind of molecule such as cyclohexane, which will behave like a hard sphere, and they may behave like a ordered structure. So you can study this kind of phase transition if you can model pretty much mica, where there is a very finite potassium ion which floats around, so you have to model well. So simulation require basic premise that the model is good. So if your model is good, you can actually predict a lot of things what you observe in experiment. So I'll take it forward. There's another example which we were very excited about is something on this freezing shift in the freezing point of fluids in confinement. So if you look at this expression is available in any chemical engineering book. If you look at it, it is nothing but it describes the shift in the freezing point. Okay, and this is nothing but the shift, the freezing temperature of the fluid in the bulk, and this is the freezing temperature of the fluid in the pore, and this is connected to the interfacial tensions and the pore width of the system and the enthalpy, bulk and latent enthalpy. So it tells you that this is a linear nature if you can have this information of interfacial tension. Okay, so it has been done, experiments have been done in pretty much into 2000, 2002. And this is oxygen, this is the indium in CPG, it's a glass. Okay, and many people have pretty much saw that this is a linear behavior. Of course, finding out the freezing temperature in pores itself is an art in experiment. So calculating such a value, you could see not many data points are there. But people were very happy that if they evaluate delta TF as a function of 1 by H, which H stands for the pore size of the material, they observe linear nature. Okay, so and this positive and negative slope is related to the strength of the material. Mica being a very hydrophilic had a positive slope, whereas the other materials were hydrophobic in nature. So anyway, so the question was that when we looked into deeply, we observed that there is some kind of a fluctuation, and which bothered, and fluctuation was occurring at a very smaller scale, like a few nanometer, less than 10 to 20 nanometers. So with this bothered us, like maybe something is going on. Okay, and then we observed that maybe the linearity is at higher, when the pore size is much higher, which breaks down at a smaller scale. So this is where we started doing a little bit more in-depth analysis that what is the picture of freezing and melting transition in nanopores. When you define nanopores, you're saying that few nanometers, less than 10 nanometers. Okay, if you want to put in terms of molecular size of the fluid, then it's less than 8 to 10 molecular size of the fluid. So, so we did extensive simulations. Again, in molecular simulation, we developed a method to calculate the melting point in a confined system. And this is one paper. Of course, we have published many papers in this thing. But eventually, the story is the following: that we show that the oscillatory nature is indeed the case when the pore size is below few nanometer. To be precise, 8 molecular diameter. If the pore size is less than 8 to 10 molecular diameter, you would see oscillation like this. And if it is higher, you would see that shift in the melting of freezing temperature of the fluid in confinement will be linear in nature, as predicted by the classical thermodynamics expressions. So this is true for all the fluids. That's something which, whether you take water, whether you take anything, it turns out that it is something is absolutely true. And the reason for this oscillation is that there is there's a lot of surface influence on the structure of the molecules comes into the picture. So that means if the surface has a square lattice or is a disordered in nature, or surface is amorphous, that's going to play remarkably on the nature of the melting or freezing behavior of the fluid inside it. And that's why this oscillation is there. Okay, which was indeed the case as in the experiment. Okay, so you can further go on. You can look at, let's say, a super hydrophobic surface. So this is an example where we actually look into, the ice formation. We look into the forms of different ices in different conditions, such as in a geo. Earth, where the pressure is extremely high, 10 to 12 megapascal, temperature is very high. We are working on a model to predict the behavior of that. We are looking at the diamond structures of those things as well, not for ice, for carbon. So one can also address such a question, whether a surface which is developed for super hydrophobic nature, can it also be anti-icing? And similarly, you can address. So we are working on this thing, which I don't want to get into the details of it. Uh, Similarly, you can also look into the nanoparticles and applications, variety of different exercise you can do. Uh, all these applications are all feasible. Need not be using only one technique. You may have to use may have to use density function theory or quantum mechanics. In that, using some tools such as the Gaussian or Espresso and so forth, and club it together to your molecular dynamics in terms of, depending on whether you would like to address one question or other question. Okay, you can also extend to drug discovery. You can also think of what kind of target molecule will be there, which will sense a specific virus, for example, or cancer cell. So all these exercises, you can try that. Of course, I'm not saying that this is trivial. This requires in-depth understanding. This requires the right kind of model development in order to do that. And more importantly, this requires working with, let's say in this case, a biologist. Okay. Okay, so let me now add a few things, few questions specifically to provide a little bit of idea of what we are doing now with machine learning. So as I said, we can look into many problems, and of course, problem definition is important. The methodology, which method you have to choose, depends on the time and length scale, and your understanding of the model is also important. If the model is not right, then you have to worry about how to develop the model. Okay, the more important thing is now that a lot of data exist in literature. Okay, so they are on the web. So how do you use the data? You may not, or you did not reproduce the data. Okay, because the data is already exists. So if you want to develop something very new, you have to ask the question that whether it's already done or not. So it turns out that, for example, in this case, we were interested in to come up with a appropriate material for ethane ethylene separation using machine learning technique. So there are thousands of data for metal organic framework. Okay, so how do we do that? Okay, I don't want to do each and every millions of simulations for the same thing, because then essentially I'm not getting anything out of it. So what would be the strategy when you have a large, ample possibilities of materials, which one to choose for a right kind of adsorbent? Okay, so let me just talk about this work, and then you will understand why what we're doing in this. So basically, ethylene is a quite an important feedstock for petrochemical industries. Okay, global production is 150 million tons, so it's $1 billion industry. And ethylene is produced by steam cracking of ethane. The major challenge is that the certain amount of ethane residue coexist in the product, and hence we have to separate it out. And cryogenic distillation is well established in this case. However, it is heavily energy intensive, and thus it is required that some alternative mechanism or method should come up. One possible way to do is adsorption based, where it should be something, the porous materials or adsorbent which we design should be easily synthesizable. It should have a high surface area and highly tunable. Okay, depending on the conditions which you would like to do. So, there have been recent effort to find out adsorbent for this ethane ethylene, and some of the adsorbent recently was published in Science, where they've used a specific metal organic framework. Okay. Now, if you look at metal organic framework database, there are millions of database which exist. Okay. So what we are interested is to find out a specific metal organic framework which can be used. And one of the desired property is that we would like to selectively adsorb uh, ethane out of the mixture of ethane ethylene. Okay, so that we can separate ethane from the ethylene mixture. Okay, and that's something which so I will just skip that. So how do you do that? So we have, as I said, we have this hundreds of materials. Like if you look at Material Genome Center, there's 8 lakh structures available. And these are all created MOF, all different things. There's a Cambridge structure data, which is 9 lakh system. There's a hypothetical MOF, which has 1 lakh 37 system. So there's an enormous number of data. So we have to, first of all, understand how to do that. And that's a pretty challenging, because there is one particular materials, a couple of them, which are extremely good and far superior than what is existing for such a system. So a typical way which we consider in a molecular simulation or machine learning technique is to prepare a database. So in this case, what we have done is we have taken our database, which is a material organic framework database, and created so one thing is you can take the existing database, you don't do much about it. Another thing is that you take the database, you understand how the database is created, and then you use the building block to come up with a new set of database. Okay, so we have done that. And then the second thing is, for each of the materials which we have fictitiously considered, and as well as those which were in the database, we calculated the properties. Now, these properties are nothing but the void fraction, surface area, chemical properties, metallic percentage, so forth. And each of them, for a certain amount of database, we've taken the subset of that and trained with a molecular simulation. So for each of them, we have done a grand canonical Monte Carlo simulation, which is nothing but a simple adsorption, desorption kind of a simulation method. And subsequently, we train a machine learning method, and then we try to predict the best material out of it. So this is a typical mechanism which we adopted. I'll just show you a bit of result out of it. So this is a selectivity of ethane divided by that of with respect to ethylene, and this is a ethane uptake. So essentially, what we are looking for is high selectivity of ethane, because we would like to adsorb the ethane out of ethylene mixture. Okay, and thus the selectivity should be also high, and the amount of adsorption should be very high. Okay, so that we can see that, for example, this one would be much good for us. Anything in this range is good. Okay, and then this is something, the data point, that means thousands of materials we have done simulation on it, and this became our database to train the model. And subsequently, we have taken another 2000 randomly selected model, randomly selected MOF, and obtained the selectivity from the predicted model. And then we also simulated, and we found that pretty well in agreement, this prediction and simulated. So that gives a strong confidence of the model we have developed. The other thing which we have done is we have also identified the features which are important in our random forest model, which in this case we have considered. And here we found that the volume fraction in the MOF plays an extremely big role. So when you look at the selectivity of ethane as a function, selective ethane versus void fraction, you can see that selectivity is highest at a certain void fraction. And it is understandable, because you would like to adsorb ethane out of ethylene, and there's a small differences in the sizes. You want a very specific range where the MOF should be in order to adsorb the maximum ethane out of the mixture. So this is what we obtain, and this is some of them became our best material. And this 4 out of them millions of data which you have considered, these 4 of them are our best candidate. And what you see here is this one is nothing but ethane ethylene mixtures here. So now essentially this technique can be adopted for various different materials. It is just an example. We are working off now in a much bigger ambitions of creating a proper database, fictitious database as well, for experimentalists to consider that. So moving forward, we are coming with a mechanism to build MOF or this kind of molecules through these building blocks. And soon we are going to also populate a database which will be open source so that people can look at it. And we also developing a code which will be open source so that students and academicians and as well industrialists, I mean, other people can make use of it in order to, come up with new ideas or new molecules for a specific purpose. Okay. So what are the challenges ahead? Again, the challenge which I again go back is that there are two type of work which people are doing. One is a discovery driven, other is a data driven. Discovery driven is something which is mainly for academic users, but data driven requires widely accepted, validated code, accurate force field, and a kind of a trained person. Okay, and that's something is currently the challenge. And this is where I feel that another couple of years will take in order to make aware of whether as a student, academician, industries to make this as a common tool. One of the big thing is to integrate the software analysis tool, something which we are trying to do that. This is necessary to make easy for non-expert. Develop and archive force field models. For example, in the case of MOF, what kind of force field I've used. And that's something is not trivial. We have, so this is something which we can build up so that people without worrying can make use of it, provided validated databases, create a molecular simulation database, integrating with process design, simulation tools for non-experts. So these are the things which are something which you will see in next 5 years, it will come in the market. Is already a lot of things are in place, but I believe that this is something which will make molecular simulation a mainstream tool and for chemical engineers, in general engineers for that. So that was what I wanted to talk about into this lecture. I would like to thank my students, former students. Some of them are already faculty in many places, and the funding agency. And basically, a lot of work which we have done is on our high performance computing system. With that, thank you for giving this opportunity for giving a brief overview of molecular simulation, a bit of what we have done and where we are going to head. Thank you very much. So I'll be happy to take any questions if there
are. Sir, I have a question.
Yeah.
Yeah, so you are talking about the confinement of a molecule in a small pores and all this thing which we are dealing with during the adsorption also and all this thing. So there is a one phenomena that when the molecule enter into the pores, they are facing some different kind of forces. So what are the properties which properties is going to be changed? One, you have talked about that freezing point and all this thing. What else properties are going to be changed?
So basically, see, there are multiple phenomena which comes into when you have fluid in confined cases. So basically, the wetting phenomena comes into picture because a lot of fluids get absorbed on the surface of it. Okay, so your densities are going to get changed, the viscosities are going to get changed. Your thermal conductivity of the fluid will get changed because they will not behave truly like a bulk system. Now, what we're talking about is narrow pores, which means basically nano confinement. Anything more than let's say 40 nanometer or let's say 40 times its molecular diameter will always behave like a bulk fluid. And I think and if you take let's say 10 to 12 molecular diameter narrow pore, you will have a layer of the fluid on the surface depending on what condition it is. I'm assuming that it is a liquid in nature. If it is a gas, then of course it will try to first wet the surface. Even if it is a little bit of hydrophilic, it is good enough to wet the surface. In that case, of course, the viscosity of the fluid will be different. The diffusivity will be different. It will start behaving, it will not be linear in nature in that sense. It will not be truly diffusive. Okay, there may be other things because it all depends. So all this property and when does it get affected depends on the nature of the surface and the scale of confinement.
Okay, thank you. Thank you, sir.
Thank you.
Sir, actually, this nanoparticles are a bit difficult to handle, right? Because they are very small. I mean, how do we perform operations on it, sir. Physically, if you want to know the diameter and all, because they are harmful for humans also, because we can inhale them, or it might go into our skin also. So how do we handle that and uh, perform operations such as this, as you said in
Yeah,
the
so
previous slide,
yeah,
sir?
so basically, nanoparticle, as you said, is pretty challenging. So one of the reasons for being challenging is that at nanoscale, you have this surface area quite large with respect to the volume, right? And then you have this surface activity, which is also prominent. So uh, now the other question is that what kind of problem you would like to study? If you want to study, let's say, a chemical reaction, then essentially you can use directly the density function theory to do that. But if you want to understand, let's say, how nanoparticles are going to affect the, let's say, viscosity, okay, such a thing can easily be handled by coarse-grained models. Okay, that's not a difficult part. Uh, but if nanoparticle is present in the, let's say, water with a lot of chemical reactivity happening, and there is another component which also play in that role, then becomes very difficult. Okay, at this point, the model will not be able to capture that. So one has to really develop the model for such a thing. It's not that straightforward. That's what I said, that the if you want to do something, you need to know how to model it. So there, your question, depending on whether you're interested in rheological aspect, if you're interested in rheological aspect, then basically you can ignore some of the reactions which are happening or some of the things which are happening, and then you can take a simple model. It need not represent in a accurate atomistic description, but you should be able to do that without atomistic description, and phenomenologically you can model it, and then you can actually explain it the behavior. Many such things can happen depending on the times and skill. So what is exact questions, based on that you have to develop the model appropriately. So for example, if I'm interested, let's say, uh, how does the flow or shear flow affects the arrangement of nanoparticle? Okay, uh, in such a case, there's no need to unnecessarily bring the complex chemical nature of the particles. Okay, a lot of things you can simply do a coarse-grained model and you can address that. You can consider, let's say, silica particle as a spherical particle, and effective interaction be considered. In fact, you can simply consider a typical repulsive and short-range repulsive and a long-range attractive interaction, and you can still address phenomenologically the behavior. Okay, but if you want precisely in terms of exact information, then it becomes very tough. Then you have to, the computation will be very, very high. So we do not foresee that this will happen in next 5 years, but you never know. Last 10 years has been phenomenal in terms of computing growth or growth of computational. And we do see, there is a possibility that such a very minute detailed analysis can be done in a normal PC. Of course, you can still do it in a large petascale computing platform, but in a standard workstation, that is not possible at all. But in future, probably such a way can be, the GPUs may be so powerful that we should be able to do this kind of thing within our laptop or desktop. So, as a methodological development, I do see that there is a need to further develop such a complex method, and there are people who are doing that. A lot of things are not in a common software, but that will come in a couple of years later, I'm sure. Until then, we would be, if you want to do just understanding of that, we would prefer to do a phenomenological models rather than a discrete, rather than a descriptive models, which is okay for simple systems. Okay, uh, I hope that I addressed the question. Yeah.
Sir, I
Yes,
have
sir. Okay, sir. I have one more question, sir. If I want to see, nanoparticles have, as you said, as a greater surface area and a smaller radius. So, if I want to use a nanoparticle as a catalyst, then how do we alter this properties, and how do we make? Because see, nanoparticles, we can't use it directly like a catalyst, sir. Because in chemical industry, we mostly deal with this one. So as the surface area will be high, then
Yeah,
catalytic
absolutely.
activity. Yes.
Yeah. So one thing you see, of course, you have to, you're absolutely right that nanoparticle can act like a catalytic agent. Okay, but you have to, at the end of the day, you have to put it in some surface, right? You have to coat it on a specific surfaces. If you want to modify nanoparticle and if you want to do this kind of model, it's not so difficult because you can in a simulation, a lot of things can be a little bit approximated. Now, of course, if I consider a nanoparticle a few nanometer, or let's say or close to, let's say, 50 nanometer to 100 nanometer, or even 1 micron, I still can understand the modification by considering it to be planar in nature, the surface. Okay, so that would be first approximation, because curvature, maintaining the curvature in the simulation is very tedious. The second thing is, since you're going to do some reactivity, so this cannot be easily handled in a classical system where the reactions are not captured in our models. So you have to go to the quantum level where the reactions are going to be taken care of. So you have to do quantum simulation. So you can do simple density functional theory for that. Okay, where you can consider different functional groups in a nanoparticle. You can try to play with the atoms. You can try to mix it. You can put another metal or of different from different periodic table. The idea is basically you can do that. However, the difficulty is the computational time will increase. Okay, you have to go to the quantum level. The alternative is that you develop a reactive force field, which essentially that is very also is pretty computationally intensive. But to develop such a model, one need to spend some time on it, and there are few groups only who are developing it. So that's a bit challenging. But quantum or CPMD or DFT, these are the methods, these are the tools which are often used in such kind of systems. Okay. I hope that I've addressed this question, because I understand what you're saying. So modifications and other surface reactivities are easily handled at the quantum level rather than on a molecular level or molecular simulation, typical molecular dynamics of Monte Carlo, until you use the reactive force field, which are very few in general. So it's not available for all the systems.
Sir,
I hope I addressed the question. Yeah.
Yeah, yes, sir, yes, sir. And one more thing, sir. Using this machine learning, how do we classify like two different components, sir? If not components, if say two particles are there, there are like different sizes and different. How do we classify them using? How say A and B like same type of different sizes, or like different. Radius. So we are judging the properties, right? So how that graph comes using this and how to identify using this machine learning, sir?
Okay, so it's a very, very good question. Okay, this is something. So we have been working for the last 2 years on this. Now we have pretty much done many works now. It's a bit challenging, because at the end of the day, you are talking about, let's say, lakhs of systems. It would be much easier if you do it simple one system and try to see whether it is good or bad. But then there's no value to that, because at the end of the day, what is the purpose of engineer, right? You would like to develop something new. Now here, the idea is that when you develop, let's say this is a machine learning. So if you look at it, what the whole thing is that there's a random forest. Of course, you can try many methods, and the question is which method works is depending on how is good your whether it's a supervised learning, whether it's a structured data, unstructured data, and so forth. So in this case, this is a property of the materials. Okay. So you have this, let's say, the number of hydrogens or carbon, nitrogen. These are part of the MOF, metal organic framework. And then you have this, the surface area, volume fraction, and diffusivity, and other aspect of that. And this is a vanadium, for example. So depending on the metal, we observe that the feature importance apparently we came up because that's where this got be correlated with the selectivity. See, the feature importance comes out of from the decision making process. So if you are able to understand the random forest method, then the decision are based on the feature. You have to take a decision, and this decision has some basic. One has to understand the basic so-called the property of the system, or the objective of the system, and subsequently the decision comes very easy. So in this case, let's say if you have to differentiate each of the system which we've considered thousands of such materials. For each of them, we identify hydrogen, how many of them are there. We identify H is there, and subsequently the data which we have generated, we try to correlate each of them. And subsequently, we found that, for example, this volume fraction is a strong indicator of this high selectivity. Okay, so the algorithms are there which identifies you, which basically plugs this information to you, and subsequently you can obtain like how much weight is given to specific property. So if you have done it a couple of times, you would understand. So this is not too much difficult once you do a simple system. And now there are many open source are there Python based source are there, codes are there, which will expedite your learning in this. So only from molecular simulation or chemical engineering perspective is to get those information on thermodynamics and other property which is a part of the material. As far as the model is concerned, a lot of things are now open source. So essentially that will help you to expedite your learning. Okay. So I hope that I addressed that question. So the whole thing is boils down to the basic the property. In this case, we calculate the selectivity, and we calculated the C2H6 uptake. So our main target property were two of them, because this is what we want. We wanted high selectivity and high uptake, because at the end we wanted to remove ethane from the mixtures. Okay, then for each of the point we wanted to see that how if you're talking about this range, okay, what is the prominent features in this material? Okay, from there we identified that, well, this is the most prominent features, and thus this model comes onto it. If you want to do a little bit backtracking, that this is what it means. Okay, the rest is a part of the algorithms. So I hope that I was a bit clear in that. Yeah.
Yes, sir, it's clear. And last question, sir. I mean, the ethane and ethene model you have taken, right? So if, for example, if any other gas is there, then that might alter the properties. Then how to overcome that difficulty?
Well, I don't want to say that whatever the model or whatever the machine learning model which we have calculated is scalable or it can be translated to any other gas system. So we can't. But what we are trying to do is we are trying to develop a automated tool which can speed up this process. So we have developed a tool just to give you an idea now, such a system which took us close to 1 year. Now we probably can do it in 1 month. Okay, so we have developed. So see, a lot of things you can automate. Okay, once you automate, your decision making becomes easier. Because then you can actually be creative. So what you can do in something in a manually, like you're pulling something, you are submitting something. If you can bring those things, if you can make it automated, then essentially you can focus on things where the creativity is necessary. So the model is not translatable, or cannot be translated to another system. But model will give us an idea that, okay, this model has worked in ethane ethylene. So propane and propylene probably it will work similarly. So we can try that. The volume fraction and other aspect, the same material will not be the good one. We have to come up with a new material. But similar methodology can be tried to similar gas mixtures.
Okay, sir. Understood.
You will start the meeting. The link that has been provided to you, you just click on the link and you start the meeting. Okay,
So any other question here?
So thank you very much. If anyone having any question, please write to us. We'll forward to the Jain Singh sir for your answer along with the contact details. You may get your question get by clear by our speaker. So I am requesting Madhu Madam to put vote of thanks for this keynote session. Madhu Madam,
Thank
please.
you. Yeah, Abhijit, I'm here. Don't worry. Namaste, sir.
Thank you.
It's my great pleasure to hear you again. Once I have heard you at my institute, and this time for the students, because this molecular simulation is an emerging area, and you have a lot of work in this area, and the student wants to work in this area. So I thought that you will be the right person to give insight of this kind of thing, because presently we are talking about the macro scale things. We are not going in molecular simulation in chemical engineering. Now it is budding area. So the budding engineer should know about this so that they can start this thing from their initiation of their career. So that's why I ask you to do that one.
Thank
And
you.
I'm very much thankful that you have given an extensive lecture on this. And the people are very happy. The students wanting to ask you many more questions, but because of shortage of time, we are not allowing them. And they will always be in interact with you. And thank you very much for accepting my invitation, because once I mail you and you have accepted, and that is the good thing of the great people like you.
Oh, thank you very much.
Hope in future also you will help us through your invited talk. And thank you very much. I'm also thankful to Abhijit. He has taken all the pain to organize this SCAMCon online, and other member of council member and students who have taken participation in this program. Thank you very much to all. Thank you.
Thank you very much for giving me the opportunity. Thank
Our
you.
presidents are also there. I would like to thanks to our president, Professor Basavarao-ji.
I have told all the team members, because this is a teamwork. We
Yes.
have worked a lot.
Thank you.
Council members as well as all the team has worked a lot to make it a success and to give a good input to the students.
Yes.
Because we want students to get something, and this is a good platform. So
Right.
I'm thankful to everyone, every member, every student, and every staff who has worked for it, along with council members. Thank you.
And I am
Thank you very much, sir.
all
Personally,
of
I
you
thank.
please join
Hello?
tomorrow's
Avijit,
keynote address.
Avijit, 1 minute.
Yes.
Avijit, I personally thank Madhu madam for inviting Professor Jayant. This
Thank
is
you,
an
sir.
excellent
Thank you.
lecture,
Thank you,
and
sir.
all our student community got benefited out of it. The molecular simulation, and you have focused on the molecular simulation and how the properties changes. So it's a very commendable research work which you have done. So I thank for sparing your time and delivering a good lecture. Thank you one and all.
Thank you, sir. Thank you.
Okay. So thank you. Tomorrow we had another keynote address from 10 to 12. Professor JB Joshi will deliver. So I'm requesting all of you, please join. The link will be available IICG Facebook page, as well as it is available in our website. So with this today concluding day, I can say that every session has completed very nicely. And though certain session has run out from the time, so okay, no problem. We are completed till now. The today's session is completed. So tomorrow morning, 8 o'clock, the first the invited talk will start. Dr. Sonal Majumdar will deliver invited talk from USA, FDA. She is the regulatory scientist at FDA. So from tomorrow morning session, it will be completed through the valedictory session, which is scheduled to be held at 5 p.m. in the evening. So all of you please join in the valedictory session along with all the special session and parallel technical session to make this event a successful ending. Thank you. Thank you all.
Abhijit, I want
Yes.
to say something.
Hmm.
Please ask students, at least students, to join these invited talks, because these are very informative talks. And I am
Right,
seeing
right.
that very few people have joined, because these are
No,
very
many
good.
people are listening, madam. Many people are watching in YouTube, because
Okay.
many people are not logging in the Zoom platform.
Okay,
So in
okay,
YouTube,
then it's okay.
more
Thank you.
than 100, 200 students are watching.
Okay, thank you.
Without logging, they can see very easily. So that's why we are providing. So all are live broadcasting in YouTube and Facebook page.
That will be fine. That will be fine. Okay.
That's why here few people are joining, but it is watching by YouTube also.
Okay,
Like in
thank
the
you.
morning, we had only 110 in Zoom, but 38 student was there or participants was there.
Wow, that's great. Good. Thank you. Should I leave meeting now? I think we should leave meeting now. Okay. Thank you. Thank you, everyone. See you tomorrow.